Solar power is a critical technology for generating clean, renewable energy. Designing and building effective solar power systems requires specialized engineering expertise. Key considerations include maximizing efficiency, ensuring reliability, and optimizing system performance. The slide shows a serene landscape with solar power turbines, highlighting the environmental benefits of this technology. As an engineer, I'm passionate about advancing solar power to help address climate change and create a more sustainable future. The sun is an abundant and virtually limitless source of energy, providing more power to the Earth's surface in 1 hour than humanity uses in an entire year. Solar power is the conversion of energy from the sun's radiation into usable electricity or heat, making it a renewable and sustainable energy source. Rapid advancements in solar photovoltaic (PV) technology, including more efficient solar cells and improved manufacturing processes, have made solar power increasingly cost-competitive with traditional energy sources. Tapping into this vast solar resource is key to a sustainable energy future. The history of solar power development spans from ancient civilizations to the modern era. In ancient times, solar energy was used for heating, cooking, and primitive solar power devices, with the ancient Greeks and Romans using passive solar design in their architecture. The modern era of solar power began in the 1950s with the invention of the first practical silicon solar cell, paving the way for the development of solar photovoltaic technology. Over the decades, solar power has steadily improved in efficiency and cost-effectiveness. Driven by concerns over climate change and the need for renewable energy, solar power has experienced exponential global growth since the early 2000s. Governments worldwide have implemented incentives and policies to promote the adoption of solar technology, further driving innovation and cost reductions. The sun is an abundant and renewable source of energy, providing the Earth with a vast amount of solar radiation. This solar energy resource drives many natural processes like photosynthesis, weather patterns, and the water cycle. Solar radiation reaches the Earth's surface as sunlight, which can be harnessed and converted into useful energy through solar power technologies. The amount of solar energy available varies based on factors like latitude, time of day, season, and weather conditions. Understanding the characteristics and distribution of the solar energy resource is crucial for designing and optimizing effective solar power systems. The photovoltaic effect is the process where light energy is converted into electrical energy. When light photons strike certain semiconductor materials like silicon, they can dislodge electrons, creating an electric current. A solar cell is a device that captures this photovoltaic effect to generate electricity. Solar cells are made from semiconductor materials and are typically arranged in modules or panels. The most common semiconductor materials used are silicon, gallium arsenide, and cadmium telluride. These are chosen for their ability to efficiently convert light into electrical energy. Solar cells rely on a p-n junction, where a positively charged layer is placed next to a negatively charged layer, allowing the flow of electrons and generating electric current. Monocrystalline solar cells are made from high-purity silicon wafers cut from a single crystal. They have the highest efficiency, typically around 15 to 22%, but are more expensive to produce. Polycrystalline solar cells are composed of multiple silicon crystals. They are easier and cheaper to manufacture than monocrystalline cells. Polycrystalline cells have slightly lower efficiency, around 13 to 16%, but are more cost-effective. Thin-film solar cells are constructed using thin layers of photosensitive materials like amorphous silicon, cadmium telluride, or copper-indium gallium selenide. They have lower efficiency, 8 to 14%, but are flexible and less expensive to produce. Monocrystalline solar cells are made from high-purity silicon that has been grown into a single, continuous crystal structure. This uniform crystalline structure allows for efficient electron flow and high energy conversion rates compared to other solar cell types. Monocrystalline cells have a distinctive, uniform dark blue or black appearance. They are the most efficient commercially available solar cells, with conversion efficiencies ranging from 15% to 22%. However, they are also the most expensive to manufacture. The image on the right shows a close-up of a high-quality monocrystalline solar cell, with a smooth, reflective surface and even illumination. Polycrystalline solar cells are a type of photovoltaic cell made from silicon that has been cast into ingots or drawn into bars and then cut into wafers. Unlike monocrystalline cells, polycrystalline cells have a multifaceted, grainy appearance due to their manufacturing process. Polycrystalline solar cells are generally less expensive to produce than monocrystalline cells, making them a more cost-effective option for many applications. Polycrystalline cells have a slightly lower conversion efficiency, typically ranging from 15 to 17%, compared to the higher 17 to 22% efficiency of monocrystalline cells. However, technological advancements continue to improve the performance of polycrystalline solar cells. Thin-film solar cells are a type of photovoltaic technology that uses thin layers of semiconductor materials to convert sunlight into electricity. They are produced by depositing thin layers of materials like cadmium telluride, copper indium gallium selenide, or amorphous silicon onto a substrate like glass, metal, or plastic. Thin-film solar cells offer several advantages over traditional silicon-based cells, including lower production costs, better performance in low-light conditions, and the ability to be integrated into building materials. They are well suited for large-scale solar power installations and applications where lightweight and flexibility are important, such as solar-powered consumer electronics and building-integrated photovoltaics. The image on the right shows thin-film solar cells integrated into the roof of a modern, clean-lined building with soft lighting. The average efficiency of commercial solar cells is around 25%, which is an important metric for the overall performance and cost-effectiveness of solar power systems. The current record efficiency for single-junction solar cells is over 30%, demonstrating the potential for advanced solar cell technologies to push the boundaries of efficiency. Solar cell efficiency has improved by around 1% per year on average, indicating steady progress in the field through ongoing research and development. Several factors influence solar cell efficiency, including the semiconductor material, device structure, and environmental conditions, which are areas of focus for improving the efficiency and affordability of solar power. Advanced solar cell technologies, such as multi-junction and perovskite cells, have achieved record-breaking performance in laboratory settings, showcasing the potential for further advancements in the field. Solar panels are made up of fundamental building blocks called photovoltaic cells. These cells are carefully interconnected to generate higher voltages and currents. The interconnected cells are then encapsulated and protected in a durable frame to create a solar module. Finally, these solar modules are combined and integrated into a complete solar power system. This multi-step process of design and construction is critical for ensuring the panel's efficiency, durability, and performance in converting sunlight into electricity. Grid-tied solar systems are connected to the local utility grid, allowing excess solar energy generated to be fed back into the grid. These systems use specialized inverters to convert the solar panel's DC electricity into AC power compatible with the grid. Grid-tied systems often utilize net metering, where the homeowner's electricity meter runs backwards when exporting solar power to the grid. This allows the homeowner to offset their electricity usage and potentially receive credits or payments for the excess solar energy they provide to the grid. Off-grid solar systems provide complete energy independence, as they operate separately from the main electrical grid. This ensures reliable power even during grid outages or in remote locations without access to the grid. Off-grid systems are custom-designed to meet the specific energy needs of the user, taking into account factors like power consumption, energy storage requirements, and available solar irradiance at the site. Batteries are a crucial component, allowing the system to store excess solar energy generated during the day for use at night or during periods of low sunlight. Many off-grid solar systems include a backup generator to supplement the solar power during extended periods of low sunlight or high energy demand. Solar power systems need reliable battery storage to ensure a consistent energy supply, even when the sun isn't shining. These compact modular battery banks are designed to seamlessly integrate with solar installations, providing backup power and energy storage. Sophisticated charge controllers and inverters manage the flow of solar-generated electricity, directing it to charge the batteries and convert it to usable AC power. These state-of-the-art components maximize the efficiency and performance of the Solar Plus storage system. Professional installation is key, including proper battery sizing and configuration, safe and secure battery bank installation, and integrated system commissioning and testing. Charge controllers are essential components in solar power systems, regulating the flow of electricity from the solar panels to the battery bank. They prevent overcharging and protect the batteries, ensuring optimal charging and safeguarding the system components. Inverters play a crucial role by converting the DC electricity generated by the solar panels into AC electricity, which can then be used to power household appliances and devices. Inverters are essential for both grid-tied and off-grid solar power systems, allowing the solar-generated electricity to be used in the home. Advanced charge controllers utilize maximum power point tracking (MPPT) technology, which maximizes the power output from the solar panels, even under varying environmental conditions, further improving the efficiency of the solar power system. Solar tracking systems orient solar panels or concentrators towards the sun throughout the day to maximize solar energy capture. These systems use sensors and motors to detect the sun's position and adjust the angle of the panels accordingly. There are two main types of solar trackers: single-axis and dual-axis. Single-axis rotate along a north-south axis, while dual-axis can rotate both horizontally and vertically. Solar tracking can increase energy output by 20 to 40% compared to fixed-tilt systems, improving efficiency and cost-effectiveness. This makes solar tracking a valuable investment for many solar power applications. Concentrated solar power, or CSP, is a type of solar technology that uses mirrors or lenses to concentrate sunlight onto a receiver, which then converts the thermal energy into electricity. This approach is different from traditional photovoltaic (PV) solar panels, which directly convert sunlight into electricity. CSP systems use tracking mirrors or heliostats to focus sunlight onto a central receiver, like a tower or parabolic trough. The concentrated sunlight heats a working fluid, which is then used to generate steam and drive a turbine to produce electricity. This allows for efficient storage and dispatch of solar energy, making CSP a valuable option for large-scale, utility-level solar power generation. The main CSP technologies are parabolic trough, power tower, and dish/engine systems, each with unique design and performance characteristics. CSP offers several advantages, including the ability to store thermal energy, high efficiency, and potential for hybrid configurations with other power sources. Solar thermal power generation uses concentrating solar power (CSP) technology to harness the sun's thermal energy. CSP systems use mirrors or lenses to focus sunlight onto a receiver, heating a working fluid that is then used to drive a turbine and generate electricity. The heated working fluid, such as molten salt, steam, or synthetic oil, is used to produce high-pressure steam that then drives a turbine and generator to produce electricity. This thermal energy conversion process is similar to traditional fossil fuel power plants. Many CSP plants incorporate thermal energy storage systems, allowing them to generate electricity even when the sun is not shining. This storage capacity makes solar thermal power a more dispatchable and reliable source of renewable energy. Solar water heating systems harness the sun's thermal energy to heat water for domestic, commercial, or industrial use. These systems are highly efficient and can reduce reliance on traditional water heating methods that use fossil fuels. The key components include solar collectors that absorb the sun's heat, a storage tank, and a circulation system to distribute the heated water. Solar water heaters can be installed in both residential and commercial buildings, providing hot water for showers, sinks, laundry, and other applications. They are particularly beneficial in regions with abundant sunshine, helping to lower energy bills and reduce the carbon footprint. Government incentives like tax credits, rebates, and feed-in tariffs help offset the upfront costs of solar installations and make the technology more accessible. Carbon pricing policies, such as carbon taxes or cap-and-trade systems, create a financial incentive for businesses and individuals to invest in renewable energy sources like solar power. Renewable portfolio standards, which require utilities to generate a certain percentage of their electricity from renewable sources, drive demand for solar power and other renewable technologies. Net metering policies that allow solar power system owners to sell excess electricity back to the grid, and regulations that facilitate the integration of distributed solar power into the electrical grid, can further incentivize solar adoption. The global solar power market has experienced exponential growth, with total installed capacity rising from just 40 gigawatts in 2010 to over 800 gigawatts by 2021. China, the United States, India, Japan, and Germany are the world's largest solar power markets, accounting for over 80% of global solar capacity. The cost of solar photovoltaic (PV) systems has dropped by over 80% since 2010, making solar power an increasingly cost-competitive energy source. Rooftop solar installations for homes and businesses are growing rapidly, driven by falling prices, improved financing options, and supportive policies. The global solar power market is poised for continued strong growth, driven by the falling costs of solar technology, supportive government policies, and increasing demand for renewable energy. As solar power becomes more affordable and accessible, it is expected to play a crucial role in the global transition to a sustainable energy future. Solar power is a renewable and clean energy source that helps reduce greenhouse gas emissions and mitigate climate change. It contributes to a healthier environment by reducing air pollution. Solar energy reduces a country's dependence on imported fossil fuels, improving energy security and self-sufficiency. The decentralized nature of solar power makes the energy system more resilient and less vulnerable to disruptions. The cost of solar technology has declined significantly, making it a more affordable option for both residential and commercial users. Solar power can help reduce electricity bills and provide long-term cost savings compared to traditional energy sources. The solar industry has become a significant source of employment, with growing opportunities in manufacturing, installation, maintenance, and research and development. Solar energy can foster job creation and economic growth in local communities. Grid compatibility is a key challenge in solar power integration. Integrating solar into existing grids requires advanced grid management techniques and infrastructure upgrades to maintain stability and manage power supply fluctuations. Energy storage limitations are another major hurdle. Efficient and cost-effective storage solutions are crucial to maximize the use of solar power, especially during low sunlight or high demand periods. Current battery technologies can be costly and have limited capacity. Regulatory barriers, such as outdated policies, complex permitting processes, and lack of incentives, can significantly hinder the widespread adoption of solar power. Navigating the regulatory landscape is a significant challenge for solar developers and homeowners. Grid integration costs are a concern, as upgrading the infrastructure to accommodate solar can be expensive, with those costs often passed on to consumers. This can impact the financial viability of solar power, especially for large-scale projects. Solar power is becoming more prevalent, so seamless integration with the smart grid is crucial. The smart grid enables real-time monitoring, two-way communication, and intelligent energy management to optimize solar power generation and distribution. This allows for better coordination between solar power and the overall electricity grid. The smart grid empowers homeowners with solar power to actively manage their energy use and maximize the benefits of their renewable energy systems. Smart home devices, energy storage, and grid interactive capabilities let solar consumers optimize their energy generation and consumption. This helps homeowners get the most value out of their solar installations. Advanced analytics and grid integration allow solar power plant operators to optimize system performance, predict maintenance needs, and respond rapidly to grid conditions. The smart grid provides real-time data and control capabilities to ensure efficient, reliable solar power generation. This helps solar power plants operate at their full potential and integrate seamlessly with the broader electricity grid. Solar power and energy storage are a powerful combination, providing a reliable and consistent energy supply. Integrating energy storage solutions, like lithium-ion batteries, with solar power systems is crucial for ensuring energy availability even during periods of low sunlight. Advanced inverter technologies enable the seamless integration of solar power with energy storage, allowing for efficient conversion and management of the stored electricity. Combining solar power with energy storage allows for better grid integration, enabling solar energy to be dispatched when it's most needed and reducing the strain on the electrical grid. Hybrid solar-wind power systems combine the strengths of both solar and wind energy to provide a reliable and diversified renewable energy solution. These systems leverage the complementary nature of solar and wind, ensuring consistent power generation even when one source is unavailable. Hybrid systems are designed with specialized components like charge controllers, inverters, and energy storage to efficiently manage the electricity flow from both sources, maximizing overall system efficiency and reliability. Hybrid solar-wind systems are particularly beneficial in remote or off-grid locations, where they can provide a self-sufficient and sustainable power source for isolated communities, telecommunication towers, and other infrastructure lacking reliable grid access. Solar power offers a viable solution to expanding reliable and affordable electricity access in developing nations, where grid infrastructure is often limited or non-existent. Off-grid solar systems can bring power to remote communities, supporting essential services like lighting, water pumping, and communications. By harnessing the abundant solar resources in many developing regions, solar power can drive sustainable economic and social development. Solar-powered agriculture, healthcare, and education facilities can improve quality of life and create new economic opportunities for local communities. Distributed solar systems empower individuals and communities to take control of their energy needs, reducing dependence on costly and unreliable fossil fuel-based power. Solar also provides opportunities for skills training and local entrepreneurship in installation, maintenance, and operations. Solar power can play a crucial role in expanding access to reliable and affordable energy in underserved communities. Innovative financing models like solar leasing and pay-as-you-go are making solar more accessible to low-income households and small businesses. Grassroots solar energy projects led by local communities are creating opportunities for underrepresented groups to participate in the clean energy transition. Investments in solar education and training programs can create new job opportunities and empower marginalized communities to participate in the growing solar industry. Solar power technology is rapidly evolving, with transformative advancements on the horizon. Innovations in photovoltaic materials and manufacturing will lead to more efficient, lower cost, and longer-lasting solar panels. Breakthroughs in energy storage, like advanced batteries, will make solar power more reliable and dispatchable. Integrating solar with smart grid systems will optimize the utilization and distribution of this renewable resource. These developments are paving the way for a more sustainable and resilient energy future. The future of renewable energy looks bright, with continued advancements in solar power technology. Solar cell efficiency, energy storage, and integration with smart grids are all improving, making solar power an increasingly viable and attractive option. As solar becomes more affordable and accessible, we expect to see a surge in global adoption, reducing reliance on fossil fuels and driving progress towards a sustainable energy future. The widespread use of solar power can significantly reduce carbon emissions, mitigate climate change, and promote a healthier, more sustainable planet for generations to come. These key takeaways highlight the innovative technology, expanding adoption, and environmental benefits that make solar power an essential part of our sustainable energy future.